Let's imagine that I have a person right here holding on to a rope. We'll say this rope is securely fastened to something like a pole. My question to you is, what would happen if this person swung his or her arms to create some sort of a wave? So some sort of a wave is generated and it is propagating this way. What happens as it reaches this pole? Well, this pole is much more dense than this rope, and it seems to be kind of a stopping point for this wave. So what's going to end up happening is, as it progresses here, it's going to hit the pole and reflect backwards. And just to be technical, it's going to reflect probably a similar wavelength, similar amplitude as well. Okay, but this is known as reflection. Okay, at this boundary, this wave kind of has a stopping point. It just goes in the other direction. Okay, now let's say I have a person with a friend. They're holding on to an odd rope that changes the density right about here. Changes from a thin to a thick rope. This person's holding on to it. What would happen if the same thing occurred? What would happen if person A is just swinging the rope like this and this progresses? Okay, well, the fact of the matter is this boundary right here holds this denser rope to the right of it. So you have a dense material over here and a less dense material. Well, just like with our pole example, it hits this pole and realizes that it's way too dense. So what's going to happen is some of this wave is going to get reflected past. Because part of this wave understands that this is more dense than the first section of the wave or the rope. So it's gonna transmit the wave, it's gonna reflect it back. Okay, but something else happens. If you notice, this rope is one continuous strand. Meaning that part of this wave does get reflected, but part of it gets transmitted straight through. So this part gets transmitted. But you would expect the part of the wave that gets transmitted to be transmitted at a slightly slower speed, or it's at least a little weaker. And that's the case. Okay, we're going to talk about refraction in this video, and refraction is simply the bending of a wave. But I want you to understand that this is all because of a boundary. Okay, this boundary is what's responsible for all these wave properties. So reflection, pure reflection, is whenever light hits a boundary and gets bounced off at the same angle as the angle of incidence was. What refraction is, let's say that wave, that light wave, gets propagated and it gets transmitted through whatever boundary you're talking about. Let's say I have two boundaries, or I have two materials, and just to be clear, these materials are both called mediums or media. A medium is any space that a wave travels through. Okay, so like light, or like air, water, diamond, glass, the earth, seismic waves are a thing. So any space a wave travels through. Let's say we have air over here, and let's say it travels to water. Okay, and since this is optics, we're going to work with light, although this can apply to sound waves and other types. But let's say that I have a light wave striking at this boundary. What's going on at the microscopic level? Well, air, you know that all these particles are kind of spread out. So if a light wave comes in here, it's generally not going to be interfered with. It's generally just going to kind of do its own thing. It's not really going to be able to strike any of these particles. But if it did, if one of these light waves happens to touch this particle and the electron absorbs it, I really don't want to get too much into this, but an electron has some sort of a vibrational frequency. It oscillates at a certain way. If that light wave happens to oscillate at the exact same frequency as that electron, the electron's just going to absorb it, never to be seen again. It's kind of the basis behind colors and why we see things and why we don't see other things. But let's say they don't match, which is most of the time. What's going to end up happening is this electron is going to absorb this light wave, but then it's going to transmit it. Okay, obviously this can decrease the speed at which light travels through things. Okay, because if a wave comes over here and it gets absorbed and reflected, then it might jump over here and it gets absorbed and reflected. Well, that takes a bunch of time. But imagine that through air, you don't have too many particles that kind of intercept these light waves. So generally, we call this optical density. We say that air has a low optical density. Now, transition is something like water, on the other hand. Well, water has all these particles that are relatively tight together compared to something like air. So that being said, light waves that travel through water are going to get absorbed and transmitted far more often. Okay? So water is going to have a high optical density. And optical density is just a property of the material that light travels through. Okay, and it's just talking about the particles. Are the particles close together? Is it going to interfere with all the light waves? If yes, then it has a high optical density. If the particles are spread out and light doesn't really have that many opportunities to get absorbed and transmitted, we say it has a low optical density. So if you go from a low optical density to a high optical density, your velocity is going to decrease. Okay, why is your velocity going to decrease? Because light keeps bumping into all these different particles. Okay, light, according to Einstein, travels at a constant speed. For our purposes, we're going to say that that speed is 3.00 times 10 to the 8th power meters per second. That's the velocity at which light waves propagate in a vacuum. It's actually slightly less than this, but for our cases, we're rounding to 3. Okay, so that's the speed of light. It's a constant c, and Einstein's E equals mc squared. But basically, light is going to travel at c through something like a vacuum, but it's going to travel at something less than c, less than 3 times 10 to the 8th, through something with a higher optical density. Okay, so back to this light wave right here. If light travels at a certain speed through air, and it's mostly c, it's mostly 3 times 10 to the 8th, although maybe just a little bit less. Through water, it's going to be slightly slower. So we know that in a boundary in a medium change, if I'm going from one medium to the next, okay, as you transition through a boundary, the velocity of a light wave is going to change. Okay, in the case from air to water, it decreases. Now, I want to bring your attention to the general equation for a wave, and I think I talked to you about this at some point. Velocity is distance over time, generally. It's some distance over some time. And we understand that with a wave, especially a light wave, the only distance that we can really gather is this distance from crest to crest, or trough to trough, and that is the wavelength. So in the case of a light wave, the distance is the wavelength, and the time is the period, which is defined as, well, the time it takes for one cycle of the wave to travel. Because velocity is wavelength over period, here's what we know. V equals lambda over p. Those are just symbols that represent velocity, wavelength, and period, respectively. Here's some math for you. If my velocity increases, what happens to the wavelength? If I have a fraction and the left-hand side increases, what happens to the numerator? Well, in order to increase whatever number this is, my numerator has to increase as well. So I know that velocity and wavelength are directly proportional. That's a fancy way of saying if this goes up, this goes up. If velocity decreases, so does my wavelength. So we know that in addition to the velocity decreasing as it goes from air to water, so as it goes from air to water, we know that the velocity decreases, but in addition, we know that the wavelength also decreases along with velocity. And this is because you're changing from a high to a low optical density. Okay? Now, here's the thing. This is a boundary. This medium and this medium, I don't really care what they are. I guess we'll just be consistent and use air and water again. If light strikes head on, okay, meaning that the boundary and the light wave are perpendicular, then that light wave is just going to travel straight through, okay, with an altered velocity and wavelength. But what happens if it doesn't strike perpendicular to the boundary? Okay, what happens if my light wave actually travels at a slight angle, kind of like reflection? What's going to happen? Well, what's going to end up happening is you're going to get a direction change. Okay, the direction of this is actually going to shift a little bit, and that shifting of directions when you transition from one medium to the next is called refraction. Okay, refraction is a light phenomenon where you have a bending of waves due to changes in optical density. I know my handwriting isn't the best, but the waves bend due to changes in optical density. So what's going to end up happening is somehow, if it does not approach perpendicular to the boundary, if it travels at some angle, it is going to refract, in addition to the velocity and wavelength changing as well. Now, this bending is all going to take place right at this boundary level. The direction is going to change at the boundary, and then it is going to be a straight ray. So to end this video, I just want to briefly talk about the comparison between the speed of light through a vacuum, which you will recall is about c, which we're going to use 3.00 times 10 to the 8 meters per second. This is a speed, so it's going to have speed units. And let's talk about the actual speed of whatever your light wave is traveling through. That's going to have a certain velocity. And in physics, what we do a lot of times is we compare these quantities. So in the next few videos, I'm going to talk about the mathematical relationship between these two. But for right now, all I want you to know is that you can actually compare this fixed quantity, the speed of light, in the best case scenario. Light travels the fastest through something like a vacuum, and compare that to the velocity. Okay, and whenever you compare these, you're going to get a number. That's going to seem arbitrary at first, but the more you work with it, the more you're going to understand what this number is. So let me just label all of these really quickly. So c represents the speed of light in a vacuum. Okay. V represents the speed of light in some medium. And n, which we're going to talk about much throughout our discussion of refraction, is called the index of refraction. So I'm going to leave you with that thought that we can compare C and V, as well as all this other stuff about optical density and what actually happens at the boundary of a light wave traveling from medium to medium. And in the next few videos, we're going to talk about the direction of bending that happens, how refraction actually takes place. We're going to look at some math relationships. So I hope this introduction, I know it was a lot, especially something as complex as refraction, but I hope that helped. And if you have any questions, please feel free to comment. Thanks for watching.